So separable is usually covered first because it's a type of differential equation that you've maybe even solved in calculus. So separable is where you can factor the right-hand side, this function of x and y, into a function of just x times a function of just y. And in that case, you can separate the x's and the y's on either side of the equality. So you can bring all the things that have a y in them, let's say, to the left, and all the things that have an x in them to the right. So you've separated the x's and the y's, and now you have two differentials which are equal. So it makes sense that if you find the antidifferential of both sides, the results should be equal as well, up to a constant of integration. Okay. So, for example, you could have x squared y minus, I guess, y. Okay, so I've written this first order differential equation in one of the kind of conventional forms we use, where we have the derivative on one side, and on the other side, on the right-hand side, we have a function of x and y. And the first thing you'd want to check for is whether you can separate the right-hand side into a function of x and a function of y. And indeed you can, right? Because you can factor out a y, and your function of x is the x squared minus 1, and your function of y is just y. And so once you recognize that it's this is separable, you go ahead and separate the differential equation. So I'll leave the dy on the left and divide by y. And on the right, the x squared minus 1 factor remains, and I just, in a sense, multiply through by dx. So that's separating the variables. And now you have two differentials which are equal. So you compute the antidifferential of both sides. Remembering that you're integrating with respect to y on the left, and you're integrating with respect to x on the right. And these will be equal up to a constant of integration. And then sometimes I mean, this is already a solution, right? An implicit solution for y. But you might want to find the explicit solution by getting rid of the log. So I'm going to have to exponentiate both sides. And the exponential and the log functions are inverse functions. And here I could use properties of exponents. So I'm using the fact that e to the a plus b is e to the a times e to the b. And this, you know, this thing is just a new positive constant, correct? C is a arbitrary constant. So e to the c will be some arbitrary positive constant. So we can just rename that. Let's call this b or something. So then y is plus or minus this arbitrary positive constant. So that just, it's an arbitrary non-zero constant. Okay. So this sort of solution with an arbitrary constant of integration is called the general solution, because in a sense, you get a family of curves or functions which satisfy the original differential equation. Okay. All right, so another type of, and you can ask me if you can tell me whether you want to next hear about first order linear, homogeneous, Bernoulli, or something from your the assignments. If you want to point out a problem, I can come up with the one that's similar. But otherwise, I'm just going to continue. That's fine. Okay. Something with a trig function? Yeah, sure. I could. Yeah, definitely. I could. I'll give you another kind of theme. So we said that one conventional way of expressing a first order differential equation is to write it as y prime is equal to some function of the independent variable x and the dependent variable y. Okay. And this doesn't necessarily have a name, but if we get not just a function of x and y, but a function of something is complicated function of x and y. It's not necessarily complicated. So for example, we might get instead of having just a function of x and y, we have a function of some expression that you see over and over again. Say x minus y plus 5. And so an example of that might be sine of x minus y plus 5, right? So the idea is to take this complicated thing and lump it into a new variable. Okay. So you would, it's the theme of substitution in order to simplify the differential equation. So you'd let z equal to this complicated expression. Again, complicated is in quotes. And then complete the substitution. So here I can simplify the right-hand side by simply lumping x minus y plus 5 into a single thing that we call z. Okay. And then you want to complete the substitution. And notice that z is a function of x and y is a function of x, right? So z is a function of x ultimately. So to complete the substitution, I would need to differentiate everything with respect to the independent variable x. So I'm differentiating the left-hand side with respect to x and the right-hand side. Remembering that the derivative of x with respect to x is 1, but y is some unknown function of x, so the best I could say is the derivative is equal to dy dx. Of course, we have a constant 0. Okay, so now let's see. We want to complete the substitution. We know that this we define to be z, but we also need to replace dy dx, and that's equal to apparently one minus dz dx. Okay. So we get 1 minus z prime is equal to sine of z. And so the idea there is that you've just simply simplified what's inside the sign, and that's going to make this differential equation easier to solve. And we see that this is equivalent to saying that dz dx is equal to 1 minus sine z. Okay, and so here now we've essentially gotten rid of y. And so we have z prime is equal to some function of, well, z. And so this is separable, right? We can bring all the z terms to the, or factors to the left. So here I would divide both sides by 1 minus sine of z, dz, and then bring the multiply both sides by the differential dx. Okay. So, and then we would find the antiderivative. So both sides, this would be equal to up to a constant. Well, the right-hand side is easy. It's the left side that we need some work. Need to do some work. So I'm not sure what to do here, but I think if I multiply by the conjugate, that should work out. Multiplying by the conjugate here is going to give you a difference of 2 squares. Which allows us to use our Pythagorean trig identity. Okay, so we know that 1 minus sine squared z is cosine squared of z. And breaking, we have a single factor in the denominator, so we can break this into two separate fractions, two separate terms. 1 divided by cosine squared becomes secant squared, and then each of these should now be easier to integrate. What's the antiderivative of secant squared? It's tangent, right? Cool. And then the second term we can integrate by substitution, so where u is equal to cosine. So we're going to get, I guess, 1 over cosine. Okay. And really, so this is sine z plus 1 over cosine z, if you will. And really, that's all we kind of need. We maybe back substitute. What is z really equal to? Remember, our original substitution was z is equal to x. What did I say? X minus y plus 5. And sometimes, so on your assignments or quizzes, whatever you're doing in your class, make sure you know, or at least ask your professor whether they expect an explicit or an implicit solution, or whether is an implicit solution good enough. So here we don't have y explicitly as a function of x, but we do have an equation relating y and x, and that's really good enough. All right. Another place this theme of substitution comes in would be if you have dy dx is equal to a function of x and y, but better than that, it's actually a function of the ratio of y to x. So in this case, we call this kind of differential equation homogeneous. Okay, and so here we can simply lump this ratio of y divided by x into a single term. So the substitution would be let z equal y over x. And then you want to complete the substitution by, finding what y prime is. So the easiest thing to do is to multiply both sides by x. And we differentiate the left-hand side with respect to x and the right-hand side as well. And then you would remember that you'd want to use the product rule on the right-hand side because you have x times some unknown function of x. Again, x is the independent variable, y and z are functions of x. Okay. So we use product rule, differentiate the first factor with respect to x to get 1 times z plus, leave the first factor alone and differentiate z with respect to x. So that's the result of product rule. And then you substitute. So you're completing the substitution. So y prime and z. Let me go here. So on the left-hand side, dy dz, dy dx gets replaced with its equivalent. It's equal to, and on the right-hand side, y over x becomes z. Okay, and this will invariably, if you have a homogeneous first-order differential equation, invariably this will become separable. And we'll see that. Just subtract z over to the right, and then you can separate the z's from the x's on either side of the equality. Right. So then you can find the antiderivative. So would you like to see an example of a homogeneous differential equation? Okay, very good. So okay, so we have y prime is equal to some function of x and y, but what's outstanding about the expression on the right is all the terms have a combined power of 3, right? So that's sometimes a telltale sign, right? So oops. Okay, sorry about that. So, if you take the power for x and the power for y and you add them, regardless of which term you look at, you would always get 3. So that's sometimes an easy way to see that you have a homogeneous differential equation. And the right-hand side, indeed, is just a function of y divided by x. So it's not always easy. I mean, part of the game here is looking at all these different first-order differential equations, being able to recognize that it's some type, right? Is it separable? Is it homogeneous? And once you do that, know the appropriate substitution or procedure to use. But if I simplify, oops, sorry, you get x over y minus y over x. So I'm going to think of the first term on the right as 1 divided by y over x. Okay, so in the right-hand side function is a function of y over x. Okay. So then we know that you're simply going to lump that ratio into a new thing called z. Next, I'm going to isolate y, so y is equal to x times z. And I'm going to compute y prime, where the prime is shorthand for the derivative with respect to x. Remembering that I need to use the product rule when differentiating the right-hand side. And then if I can write this as y prime is 1 over. You see the substitution. Y prime becomes z plus x times z prime. And on the right-hand side, these guys are z, so 1 over z minus z. All right. So, and this again, you want to know that if you have a homogeneous equation like this, if you correctly do the substitution, you should get something that's separable. Maybe I can find a common factor here. I mean, a common denominator. And I hope you see this as separable, because I can bring all the z business to the left. And all the x business to the right. Okay. And then we would, two differentials being equal, we anti-differentiate. Let's see what we get. On the right, I believe it's some sort of log. So let's just guess. Okay. So would that be right? We have to divide by -4. Okay. I would probably multiply by -4. Take my time. Now, -4 times an arbitrary constant is still an arbitrary constant. So we're just going to lump the constants along and use properties of logs, rather. And then we would get rid of the log by exponentiating both sides. Remembering on the left, I mean, what's the common mistake would be, so this is wrong, what I'm about to write. The common mistake would be to write this as plus and constant, right? Why is that wrong? Because I'm not correctly using the properties of exponents. E to a plus b is e to the a times, not plus, e to the b. So, okay, but anyway, we got rid of the logs by exponentiating. And e to the c is just some arbitrary constant. Let's call it maybe a. And here just get x over 4. All right. So we can say that dropping the absolute value bars, you get plus or minus a. So, but again, if a is an arbitrary positive constant, plus or minus a is just an arbitrary non-zero constant. So, and then back substitute. We know z is really y divided by x. And maybe you can try to solve for y explicitly by just doing some quick algebra. Okay, so divide by 2 and take the square root. Okay, so all right, so that's a general solution because we have this arbitrary constant. And so we have a whole family of curves which satisfy the original differential equation. And so what do you call what's the name that we use when we get when we have an initial condition? How do we use the initial condition? So this is like we don't know what the function y is, but we are told that's plug in, yeah. So, but we are told that at a certain value of x, y is equal to some number, say negative 2. So that's called an initial condition, and you use it to solve for a, the arbitrary constant. Okay, and of course this just says that when x is 1, y is negative 2. So as you said, you plug in. So any place you see an x, you get to replace it with a 1. And any place you see a y, it becomes negative 2. All right, so then we get something like and we can solve for a. And also, once you have an initial condition, actually, you can figure out whether you should be using plus or minus, right? So even though there's a whole family of solutions satisfying the differential equation, once you get an initial condition, you get to use it and you pick a specific function from that family of solutions. So notice here that y has to be negative when x is 1. So you have to choose the minus sign. And what is a anyway? Well, so a would be negative 7/2. It doesn't matter. Right, but now you can say that y is equal to the negative to ensure that the initial condition is satisfied of the square root one half x squared plus 7/2 divided by x squared. And that would be a particular solution satisfying the differential equation with the given initial condition. So far we looked at separable, we looked at homogeneous, and so we should next probably look at first order linear, I believe. That's also in your homework. Or, right. Okay, so when the first exam comes around, I guess what you want to be able to do is kind of keep a checklist, a flow chart almost. Right, so you have a differential equation written in this conventional form, and the first thing you would ask is it separable? So can I write it as, can the right-hand side be written as a function of x times a function of y? Can you separate the variables? If yes, right, then you just separate the variables and you integrate both sides, and you get some kind of implicit solution. So you just integrate, and these would be equal up to a constant of integration. But if the answer is no, maybe you want to check whether it's homogeneous, right? So can the right-hand side be thought of as a function of y divided by x? And if the answer is yes, then you know that you have the substitution where you make y divided by x equal to z. And invariably, if you do this correctly, you should get something that's separable. But instead of y, you'll have z. And if it's not homogeneous, then maybe you want to see whether it's the right-hand side is a function of a simple, let's say, function of a combination of x and y, and some constant there. And again, if the answer is yes, you simply lump this expression into something called z, complete the substitution, and you should get something that's separable. Okay. But not everything fits into these three basic categories. So maybe next we'd want to look at first order linear. So this is when the right-hand side can be written as some function of x minus some function of x times y. So this is first order linear. Sarvan, if you have any specific questions you want to ask, you can go ahead and do so, because you're the only one here. Okay. So now we can look at first order linear. And depending on, where your professor's from, where they got their education, and the book you're using, the notation might be slightly different. But are you still using the Prima book for your course? Yeah, I think I have a copy of the flowchart I'm kind of thinking about. Let me show you. I think I have it. I can probably send you a copy. Okay, let me share something with you. Oh, which book are you using for your class? Is it still the book by Prima? And guess who's the author of the book that your class is using? Hmm. me share. Okay, so voice and D prima. Okay, great. So it's the same book. But let me show you this flow chart. It's slightly different, but it's essentially this idea that for the first exam, which is mostly going to be first order differential equations, we're checking whether separable, this is written in a slightly different form, in differential form, and then maybe linear, Bernoulli, homogeneous, whether the right-hand side can be written as like a simple combination of x and y. And in all those, once you recognize your differential equation as one of these types, there's an appropriate procedure to use. So separable, you separate. Homogeneous, you do the certain substitution, which turns this into separable. Okay, and what I wanted to go over right now is this linear case, like this, and then the next would be Bernoulli. And this would be like the crux of the first exam. So first order linear is what we're going to look at next. And I'll use your book's notation. Okay, so first order linear. I'm going to write this like so. That's in the conventional form. Like so. So here, the idea is that there's something called an integrating factor. I'll use mu as the symbol for integrating factor. And I'll just give it to you for now. We'll see why this works. So the integrating factor is a function of x, and it's defined to be e raised to the antiderivative of the function of x that multiplies y. Okay, and what you want to notice about it is if you differentiate this integrating factor with respect to x, you're differentiating an exponential function. So you're going to get it back. But then you have to multiply by the derivative of the exponent. And what happens when you differentiate an antiderivative? Right? You just get rid of the antiderivative, so you just get p. So you just get p. And once you have the integrating factor, its job is to multiply both sides of the original differential equation okay. And so what you want to notice is that this over here is exactly mu prime. And then you say, well, the left-hand side is just applying the product rule. Right, essentially the product rule. So in the integrating factor, once you know what it is, it multiplies both sides of the differential equation. and invariably the left-hand side, but by design of the integrating factor, the left-hand side is the result of applying the product rule to mu times y. And once you know that, you can just integrate both sides with respect to x, or whatever the name of the independent variable is. And of course, integrating the derivative just gives you their inverse processes. So you just get mu times y. Now, do you know the other method? What's the other method? And so then there's just one last step here. You just divide both sides by mu. And what you have is, in fact, a nice formula for solving for x. Yeah. So you're probably deriving. So I said I'm going to give this to you, right? But your TA probably derived it. So I was first going to just outline the procedure. So if you write your first differential equation in the standard form, where P and Q are functions of x, you recognize this as a first order differential equation, and then you know a formula for the integrating factor, and then once you have it, you have a nice explicit solution for y. So in a sense, this is all you need, except your professors might expect you to be able to kind of do the whole procedure. So I think we should maybe do an example of this, right? So let's do an example. And okay, so here's a differential equation where the independent variable is t this time, not x. Right? A lot of this stuff comes from physics. And so we have things being functions of time. Okay. So the first thing you'd want to do is make sure that it's written in the standard form before you correctly identify the integrating factor. So notice that in this standard form, y prime is being multiplied by 1. The coefficient is 1. So we first have to divide everything by t squared in order to get our differential equation in that conventional form. And you recognize this as first order linear. So we know that we can define the integrating factor as e raised to the power, which is the antiderivative of this function of the independent variable that multiplies the y term. Okay. I'm just going to assume t is positive. So it looks like at the end of the day, the integrating factor is just t squared. Okay, so the job of this integrating factor is to multiply both sides of this original equation. So multiply both sides by t squared, which was kind of stupid because that's what we started with, not that I look at it. But the idea is that invariably this left-hand side is the result of applying the product rule to the integrating factor times y. It's the beauty of the design of that integrating factor. And so to undo that derivative, we just simply anti-differentiate both sides. We're finding the antiderivative with respect to the independent variable t. So we don't have to do anything really on the left-hand side because the antiderivative undoes the derivative. On the right-hand side, it's an easy enough integral. And don't forget that constant of integration. And now we can divide by the integrating factor t squared on both sides to get an explicit solution for y as a function of t. So that's a general solution. And if you had an initial condition, say y of pi, right, you plug it in, that's right, whatever, 0. So c would be 0 in that case. We can plug in and solve for c. That way we have a particular solution satisfying the differential equation with the initial condition. All right, did your professor already talk about Bernoulli Bernoulli differential equations? Okay, so Bernoulli, the idea is that it's not quite, it's a differential equation that's not quite first order linear. It's not, but it's close, suggestively close. Okay, so with first order linear, we could think of it as writing in standard form. Looks like this. P and Q are functions of the independent variable. Now Bernoulli is where you have that, except on the right hand side you have some power of y. So it's not a linear differential equation now. So that's Bernoulli. That's how you recognize Bernoulli. It kind of looks like first order linear, but it's not because of this y to some power. And in that case, it turns out that if you use the substitution z equals y to the 1 minus n, then if you correctly complete the substitution and get rid of all instances of y and y prime, you're going to get a first order differential equation, a linear differential equation. So you kind of reduce the Bernoulli case, which is nonlinear, by using the substitution into the simpler, into a case which you know how to deal with, the first order linear differential equation. I mean, the Bernoulli is a first order differential equation, ordinary differential equation, except it's not linear because of this. But using the substitution, you'll turn it into a first order linear differential equation. So maybe let's look at an example. For Bernoulli. So you might have so that looks complicated, right? But it's definitely not linear. I mean, I guess technically I would first check whether it's separable, but it's not, because separable is so easy. So I was going to glance at it. It's not separable. It's not homogeneous because of the cosine of x for sure. So it's none of those. So I kind of go down the checklist, and I go, well, I'm just going to write it in kind of standard form. So let's see what we get. Y prime. You know, that's not a cubed. That's just an x. Okay. And so I recognize that if we just had this would be first order linear, but we have nonlinear because of this y to the negative 2 power. So you recognize that as Bernoulli, where the power for the y on the right-hand side is negative 2. So let's see what happens if we let z equal to 1 minus n. So in other words, z is equal to y cubed. And let's try to use that, let's try to complete the substitution by getting rid of all instances of y and y prime. Okay. So I am going to, let's see, what can we do? Okay. I'll go ahead and differentiate both sides with respect to x. And remembering that z and y are functions of x. So you have to use steering wheel. Implicit differentiation. Okay. So let's see. The way, and there's many ways to do this, but what I see is that, let me highlight what I'm trying to refer. I have a y prime over here, and I have a y prime over here. So what I'm going to do is actually multiply both sides of this differential equation with this by this factor. I'm going to multiply everything by 3y squared. Okay, so you get that. Okay, so then 3y squared times this business. And 3y squared, oh, you can't see that, can you? Yes, you can. Times that business. So the y squared times y to the negative 2, that's y to the 0. So that goes away. And now notice that this is exactly z prime, according to this, right? And y cubed is z. And on the right-hand side, there are no y's left. So indeed, now this is first order linear, where, you know, instead of y, we have z. Hey, Luke, what's up?
Howdy.
Hey. Are you in this class?
No, I have a weekly review at 1. Yes.
I see. Okay. All right, so now we can then revert to our procedure for solving a first order linear differential equation, where we see our integrating factor is e raised to the power, which is the antiderivative of the function multiplying z. So I believe that this is x cubed. So our integrating factor is x cubed. Okay, and then we use the integrating factor to multiply both sides of our first order linear differential equation. And we observe that 3x squared is exactly the derivative of x cubed. So really, the left-hand side is just the result of applying the product rule to the integrating factor times z. And we then we deprime the thing, so to speak. We get rid of the derivative by integrating both sides with respect to x. These things are going to be equal up to a constant of integration. And then lastly, we solve for z by dividing by that integrating factor. And then remember to back substitute. We know that z is really y cubed. Anyway, you have some implicit solution. Okay. And I don't feel like doing integration by parts to compute the integral of 3x cosine x. Okay. So in summary, and I think you can find the flowchart I shared on our e-learning site if you go to helpful documents. Okay. Let me pull that up again. Oh, okay. I wasn't able to control my mouse because I had the stylus near the screen as well. Okay. So I'm referring to this flow chart. Again, it's like the better thing the way I think of it is that you should be able to create such a flow chart before your first exam by recognizing the different types of differential equations and either the correct method of solving it or the correct substitution, which will simplify the original differential equation to one that you know how to do. And next time, I guess we would be looking at exact and inexact differential equations and integrating factors which help you solve those differential equations. Okay. Okay, thank you. No problem. Let me see let me go to e-learning and see where it is exactly, because I didn't put it there, so I don't know its exact location. Get that. Okay. Oh, there it is. It should be in resources for students. and differential equations, and it's differential equations flowchart for the first exam, really. That's a bad copy of it too, but whatever. Okay, cool. Very good, thank you. How's your connection, Luke?
Seems to be on point today.
All right. I thought my review was at 1, so I kind of messed up, but
Oh man.
for some reason I had it at 1 on my calendar, so I think I just somehow transposed your review and my review, or
Oh god.
either that, or the time was changed and I wasn't aware of it.
Hey, you're still sharing your screen.
11:30 to 12:45. How are your classes, Luke? What are you taking?
I'm taking probability. I'm taking discrete math and combinatorics.
Oh, nice.
And I'm taking physics 1.
Are you taking the 4,000 level probability?
Yes.
Cool. Are you liking the discrete math? The combinatoric stuff?
Yeah. Yeah, it's pretty cool. Can you hear me?
Yeah.
Okay.
Did I stop recording? No, yeah. Is it still recording or no? Yeah, it's still recording.